Okay, so
Yeah.
yeah, today we'll be talking about NFNets, which is an advanced image classification model, and we'll look into how, like, this is actually pretty new. It came out like a few days ago. This paper was launched a few days ago, and yeah, like we'll be looking into the model and how it's better than the previous models, and what extra does it provide, basically. So first, we'll start with what image classification is. So basically, in the machine learning field, there's a there's a section called computer vision where everything related to uh, basically what we see and how we depict which is what, and which one is further away, which one is closer, how they are different from each other. uh, it's basically that, but for computers. So one of the most common doubts in computer vision is the difference between image classification, object detection, and image segmentation. So you might have heard like few of them in the previous sessions as well, like mostly object detection. I think there were around two to three this thing sessions related to that, and few of image classification as well. But today we'll be again concentrating on image classification. So let's break down these terminologies so that uh, one by one we'll learn what the difference is. Starting with image classification. So if you look at this picture at the center, uh, you will know that it's a dog. If you like, you'll realize it's a dog. So you need to know how you came into that conclusion. So basically, you know this is the dog because you have seen dogs, you have seen creatures that look like this and are called dogs. Maybe not the specific species or anything, but you know it's a dog. Okay. So your brain realizes that because you have looked at, because you have growing, you have looked at so much, you have had so much experiences, you have looked at so many things, and then it has learned that, like simply, if I show you this, you will definitely know it's a dog. If I show an alien which you have never looked at, or maybe even an insect, very new species of an insect, you might think it's an alien, or it was photoshopped or something else. Okay. So as you saw, there's only one object there, which is a dog, which is very easy for image classification. This is where image classification comes in, where it needs to recognize what is there, prominently what is there in that particular image. So what if there's more than one animal in the image? Like in here, there's a cat and dog. So we will need to require a multi-label classifier where it tells, like if you feed this to image classification, it might say animals, or because dog is covering most of the image, it'll say dog. But because we know there are two images, so we can go more in depth to the computer vision technology and use a multi-label classifier so that it can detect what all animals are there, what more than one, and where they are located. That's where image localization comes in picture. It basically helps identify the location of a single object in the given image. So this is more advanced than image classification, but then it also takes more time to calculate it. So yeah, in case we have multiple objects present, we can rely on object detection, which we have learned in the previous sessions. So here, image localization is used, where there's only one creature, one type of creature in the image, and if there's multiple creatures, multiple types of objects, we can use object detection for each object. Now, before detecting the objects, even before classifying the image, we need to understand what the image consists of. This is where image segmentation comes in. So basically, before any of the previous tasks happen, it's important for the image to be segmented into smaller boxes, so that it basically calculates which part of the which box contains what object. Like let's say for this example, this dog is this whole image is basically broken into multiple small boxes, and then you'll see like this edge is connected to this edge, this edge, this edge, but this box won't be connected to this one. So we will know that this is one particular object and this will be another particular object, this being in front of this one. So that's where segmentation comes in. And yeah, like after segmentation is basically the classification detection comes in place. So to quickly summarize, image classification helps classify what is contained in an image. Localization specifies the location of a single object. Object detection specifies location of multiple objects. And segmentation will create a pixel-wise mask for each object in image. So now that we are clear with the differences, we can go in depth of how image classification works. So image classification is basically a supervised learning where like a set of defined targets are there. Basically the objects that needs to be identified, and a model is trained to recognize how to label each object in that image. In early computer vision models, it relied on raw pixel data as input of the model. However, raw pixel data alone doesn't provide a sufficiently stable representation to encompass the myriad variations of the objects as captured in image. Because in the earlier computer vision technologies, it looked very much in detail rather than the big picture of what is there in that image. So it was like if you only look towards into the details of the image, then you might think that if there's two objects, they might, because the shades might be similar, you might consider that whole object as one object. So that was the issue. And yeah, like the position of the object and the background behind the object, lighting, camera angle, camera focus, like there were multiple variables that need to be taken into that needs to be taken into mind when calculating such things. So the model objects more flexibly to model objects more flexibly, classic computer vision models added new features derived from pixel data such as color histograms, textures, shapes. So it basically learned what is existing, like giving multiple millions of data. Well, initially not millions, but now there's millions and billions of data. But yeah, and then the more data it's getting fit, it's also learning as well. But the downside of this approach was that feature engineering became real burden as there were too many inputs to tweak. Like as I was saying, like initially there were thousands, tens of thousands, hundred thousands data, but then now since there's more data, obviously it might increase the prediction, the accuracy. But then because there's too much data, it's very hard to like label them, because this is a supervised learning. So a person needs to teach the computer. It can't learn on its own. So for a cat classifier, let's say, it needs to take into action which colors are most relevant based on the knowledge that it has. How flexible should the shape definitions be? Because features needed to be turned to so precisely building robust models was quite challenging and accuracy suffered. So yeah, like as in some memes, you will see like cat, it can fit into anything. So it's almost shapeless. It's like water. So that's basically like kind of a joke where it comes in the classification model. And yeah, so here's a look into the existing classification model, like the top performing ones before NFNet. So here there's noisy, efficient net. It took the dataset of ImageNet and the accuracy was around 88.4%. Then ResNet dataset was CIFAR 10 and accuracy was around 99.3. But actually, like not just looking into the accuracy, the efficient net was actually better because it took less time to basically predict. Although the accuracy was low, it took less time and to train and to predict as well compared to ResNet. ResNet, it took more time. So time and accuracy both comes into the calculation for which one's better than the other, and there were some other as well. So we'll compare efficient net and ResNet, and how like the new model is slightly slightly more evolved than these two, and how they're similar as well. So the new image classification model was provided by Deepmind. Like one of the most annoying things about training a model is time it takes to train it and the memory needed to feed the data and the models. So these are the two main, what do you say, the main issues, the main problems that any, what do you say, any training any model takes place, like whether it be image classification or any type of model. Since image classification is one of the most common machine learning tasks, DeepMind released a new model that matches the state-of-the-art performance with significantly less size, higher training speed, and fewer optimization techniques for simplicity. So it basically, because of the previous models, what they were facing, what issues they were facing, they basically tried to remove them, like being less, taking less memory, increasing the training speed, like taking less time to train, and some few optimizations. Like compared to previous ones, there are multiple optimizations. Basically, we'll come to that. But then in NFNet, there was actually, they removed a few optimization method techniques, and it's still gotten better than the previous ones. So in this work, they examined the current state-of-the-art models such as efficient nets and ResNets. In their analysis, they pinned down some of the optimization techniques that utilize a lot of memory without producing a significant value in performance. So you could say like this model, in the end, you see like this model had the almost this around the same accuracy at efficient net, but with lesser time and lesser memory to take into action. So prerequisite batch normalization. So yeah, like in most of the previous models, you see batch normalization being used. Like it's kind of like a important step for used in training the models. So the paper starts off with an analysis of batch normalization. Like batch normalization is being used almost in any training of any models, like most of the models basically. Although it has shown great results and has been used heavily in tons of state-of-the-art models, it has several disadvantages outlined by the paper. So like disadvantages being it's very expensive like the computation cost, like it takes way more time because of that. Like obviously it helps in the precision and prediction, like fast, higher prediction, but then it costed a lot because of that. Then it had a lot of extra hyperparameters that further needed fine tuning. It caused a lot of implementation errors in distributed training, and it performed poorly on small batches. Like batch normalization is basically for data sets that, like huge data sets, basically. It takes the data sets and convert it into smaller batches, which helps into training, like iterative training for those batches. So for smaller data sets and smaller batch sizes, it caused quite like some issues, basically. So by removing batch normalization, we need to understand what benefits it brought to the models, so as to find a smarter way to still have those benefits, but with fewer cons. So the benefits that batch normalization provided were, it downscaled residual branches in deep ResNets, like in the previous one, that in one of the previous models. So ResNets are one of the most widely used image classification data, and like it had thousands of layers. So it basically helps downscale the branches. And then it also eliminated mean shift for popular activation functions such as ReLU and GELU in large networks, which also came into use in the efficient nets. So there are some other benefits, but it's mainly about regularization and smoothing the training process. So the new net model that came out was NFNets, Normaliser free networks. Like because they removed batch normalization, they are calling it Normaliser free network. Although there have been previous attempts to remove batch normalization in various papers, the result didn't match the state-of-the-art performance or training latency and seemed to fail a large batch sizes. This is the main selling point of this paper. Like in the previous papers, there were attempts for the same, like removing the batch normalization and seeing how it performed and all. But then it wasn't up to the mark, like compared to the ones with the batch normalization. So they proposed a gradient clipping technique called adaptive gradient clipping. Essentially, gradient clipping is used to stabilize model training by not allowing the gradient to go beyond a certain threshold. So it kind of works similar to what batch normalization did, but in much a simpler way. Like batch normalization basically uh, reduces the large data set into smaller batches. And here is basically what's in AGC, it's what it's doing is basically clipping the gradient so that it remains at a certain limit. However, the main issue is setting the threshold hyperparameter, which is quite difficult and manual task. The main benefit of AGC is to remove this hyperparameter. So they have found that through multiple experiments, it's much better to use a unit-wise ratio of gradient norms instead of layer-wise ratio. Layer-wise has always been used in the models, but they decided to go with unit-wise ratio because each layer can be more than one gradient. In addition to this, they also use dropout to substitute the regularization, which is which is common. Dropout is being used almost in any model, but yeah, like they also use that. And they also used an optimization technique called sharpness awareness minimization. It basically reduces the residue from the layer, and this is basically mostly for the finer details in the image, in the data. So basically, they divided this model into two parts. The smaller models match the test accuracy of the efficient net on the image net, while being up to 8.7 times faster to train. And the largest models attain a new state-of-the-art accuracy of 86.5, which was like slightly lower, but then if you combine them, it's basically the same as the efficient net model. So final thoughts, image classification. About image classification, basically the tasks occupy the majority of machine learning experiments. The critical usage in medical diagnosis, digital photography, self-driving cars, and many other have attracted researchers to innovate models that would give near perfection prediction of the target object. And like mostly like who would have thought that replacing some minor optimization techniques such as batch normalizer, which has been used almost in every model, would result in 9 times the improvement in the training latency. That were basically the final takeaways from this. And now we'll look into a demo. There's a public demo that's already present. Anyone can use it. So I'll just share my screen again. Is this visible?
Yes.
Okay. So in the references, I have provided like how to access this notebook, Python notebook. And yeah, like, so basically here, it's kind of like a dry run how this model runs. It's already been pre-trained. So we'll just directly go to the testing part. So here, it already cloned the repository, which consists the code. And in the class list, you'll see like they have like around 1,000 different classes, different labels for what do you say? Like this is actually limited. There are much more, but then they only kept 1,000 for this demo. Like goldfish, tiger shark. These are types of some fishes. Then rooster hen, some birds, again some fishes. Like mostly animals you'll see, and then some parasites as well, and some animals, dogs, cats, and all. Like even types of dogs you'll see. Also some locations like some vegetables you'll see, some locations you'll see, like a gas station or something like that. And some objects as well, like baseball, basketball, instruments and all. So these are the things that they have set for this, like these are the labels that they have set for this training, this example. And then it's basically loading the model. I'll just going through one by one the code, how to run it. These are loading the weights and then grabbing an image from online. We'll see what that image is. And then we're providing the prediction. Basically predicts which class it is. So here's a bell pepper or capsicum. And if I change the input image to this one, Then, because see, here there's more than one object, like you see cut off of bell pepper, tomatoes, and cucumber. It's taking the cucumber into it's classifying it as cucumber because that's the majority of it, and like the one that is most in front of it. And then there's another example we can take. A value. So yeah, like this can be accessed. This is in public repository. And yeah, I think, yeah, that's it for the presentation. Any questions? Any doubts? Okay then. So thank you for joining. Then yeah, thank you for your time, and we'll again connect next week for the next AI session. Okay, yeah, that's it. Bye bye.